everyone. Welcome to another one of our webinars, part three of our CMHC MLI Select process webinars. This one is about building performance requirements. We're going to wait a couple minutes for everyone to join. Do us a favor, go into the chat box on your side, type in your name, and tell us where you're joining from. We're going to wait for a couple minutes for everyone to join in. Just want to make sure you can hear us and also you know how to use the chat box. Please type in your name, where you're coming from. From Kitchener, Nikhil, pleasure to have you here. Samantha, Ajax, hey Paul, good to see you. Slobodan, hey Slobodan, from Ottawa, good to have you. Former presenter at one of our webinars. Michael, hey Michael. And Tella from Toronto. Okay, perfect. Good, so you can hear us and the box is working. Mariana, pleasure to meet you here. Anyone else? We're going to wait for another 30 seconds. Hey, Justin. Thanks for being here. Okay, let's dive in. My name is Payam Nur Salehi. I'm the president of Dental Project Management. I founded this whole thing about midrise.ca a few years ago, and we provide information, best practices, and industry experts. We bring them in to share their experiences about midrise projects, how to build new projects, and we help them through. We help developers bring these projects to life, and hope you find it useful. If you do, please share it with others. Hey Saba, thanks for coming back here. For those of you who are new, this is a three-part webinar series. This is part three of the three-part series. The part one was about accessibility requirements. The second part was about financial requirements, and the third part is about building performance requirements. The past ones, you can go on our website. The replays are free. You can just go there, grab the replays, grab the slides and see the replays. This one will be no different. Once we're done, we're going to upload it there on the site in the next couple of days, and you can see it there. Sorry, can you hear me? Okay, perfect. Sorry, I lost you guys for a second. What is CMHC MLI Select program? Again, very quickly, CMHC is a program that ensures the mortgage loans that are offered by different mortgage brokers and lenders throughout the country. It's based on a point system that gives points to affordability, energy efficiency, and accessibility, like the titles of our previous webinars. And the better points you get, the better rates you get. Before we get started, just so we have a better understanding of where you guys are coming from, tell us a little bit about yourself. There's a poll in your chat box. Please just take a second to answer that. Okay. What stage is your project at? Okay, good. So we still have time to fix things. Third one. Do you know what you're aiming for? Okay. For those of you who are not sure, we're going to help you find out your targets today. That's why we have the experts on board. And one last question. For those of you who are a little bit ahead in your journey on your project. Okay. Perfect. Okay. That gives Kara a little bit more ammunition, talk about the systems down the road, and Scott a little bit more context. Our presenters today are Kara Sloat from Hamstag and Jaffe, and she's been around for quite some time. She can do her own introduction. I won't dive into it too much. We have Scott from Intuitive, and he is specializing in building sciences, and he's going to talk about energy modeling, energy requirements. Again, they will do their own introductions, and with that said, I'll turn it to Scott. Scott's all yours.
Great, thanks, Payam. You can hear me okay?
Perfect.
Okay.
And sorry, just for everyone's purposes, if you have any questions, feel free to type it in the chat box as we go through, and we'll gather them together and we'll present them.
Okay, great. Thanks, everyone, for joining. Very excited to be on this webinar and to talk through a little bit about the building performance aspects of the CMHC MLI Select program. I am a senior associate at Intuitive. I have a part role in building envelope services as well as in the sustainability group. So trying to bring those two together in a very unique and powerful way to help us build better buildings and deliver a low carbon future. I'm going to talk very briefly about energy modeling. Just on the requirements for CMHC MLI Select, these are, again, very high level. There's no indication of future changes, although it is reviewed annually. So it is possible that something might change. But as is maybe familiar with several people, there are 3 primary levels, 20 points, 35 points, or 50 points based on a 20, 25, or 40% better than NECB 2017. There are compliance paths that are also associated with other third-party standards and certification programs like Passive House or ZCB, Step Code, Toronto Green Standard, and others. What I am a bit unclear on, to be frank, is whether thermal bridging is a firm requirement by CMHC MLI Select. In my opinion, yes. I think in some others' opinions, perhaps no. So I'll talk a little bit about what that implications of that are, and that will certainly affect the energy modeling results and process. So what do you need to do for energy modeling in order to get your application approved? There is a design assistance during the design phases for the energy modeler to provide some feedback and or an envelope specialist who's sort of part of that team. The preliminary results go in at the SPA submission, and there is another final submission at the building permit stage. So there's sort of like 2 submissions there. And then it's an energy modeling report and an attestation letter. So it's basically saying, yes, we followed all the CMHC MLI Select requirements. We've done the modeling in accordance with those rules. Here are the targets that we're meeting. And that letter gets signed and submitted with the package. So that's generally the process for energy modeling. I'm going to spend most of the rest of my time talking about the envelope performance. Happy to take some questions on the side and maybe chat with a few of my other colleagues if I can't answer anything specifically. And Kara may also chime in when she delivers the M&E portion of the webinar. Okay, so what are we talking about with the building enclosure? Again, to focus on, we've got about 50 points to work with here. And it does, we are able to hit that 50-point threshold with a really good building enclosure as an enabler to an amazing mechanical system. I see us working very much in concert with each other. We are an integrated system, envelope and HVAC. And in my opinion, again, envelope really sets the stage upon which you build amazing low carbon mechanical solutions. I put in here a couple of images that I've taken while walking around various towns. I can't help myself but take pictures of buildings and other things like sewer grates and weird details and things that kind of intrigue me. So these were some of the nicer photos that I found, not sewer grates. But so just sort of an example of some of the building types that you might see in that kind of higher tier performance. These are mid-rise or low-rise buildings. I have a couple of other examples from high-rise buildings to give you an example of what you might see in terms of a built form for fenestration to wall ratio, opaque cladding types, et cetera. I'm going to bring this back to the basics on what are some principles that we apply whenever we look at building enclosure design, but specifically when we're looking at high performance building enclosure design. I'm going to leave this, I put this up first, but it really is kind of the handoff to Kara on, making sure we're ventilating correctly. That's a totally separate discussion. I'm going to focus on the building enclosure performance. We want good thermal insulation. So we want a good continuous non-bridged thermal blanket around the entire building envelope. That includes all sides of the box, including the bottom. So again, being very mindful of overhanging floors or things in contact with grade. That is also a very important surface to insulate. We want to make sure we don't have anything bridging through that thermal blanket that is not mitigated in some way. And I'll talk a little bit about how that is achieved, as well as the implications of not doing so. We want great fenestration. We don't necessarily need passive house level style windows, and I'll talk a little bit about different window performance, but we want very good windows. And connected with this thermal bridge reduced design aspect, we want them to be installed well, and we want them to be aligned with the insulation, and we want to reduce the amount of thermal bridging that's happening at the transition from windows to walls. I'm going to have another thing I want to mention I'll get to when I talk about thermal bridging, specifically with the window and the impact on thermal bridging. And then lastly, and certainly not the least important, is air tightness. In fact, probably one of the most important aspects of good building design and good building enclosure design is focusing on air tightness in design, making sure the design teams are aware of it, making sure your specifications include targets and strategies, making sure that you talk about it in construction, making sure that you assign responsibility to this to someone so that there is accountability. And then we could talk a bit about measuring air tightness as well. So again, very basic level in terms of many people familiar with this, but just to bring it back to basics, these are the steps that we follow to achieve good building envelope design. Again, this is getting back to helping us understand the framework for talking about insulation. We have nominal R value, which is that number that's stamped on the product that you buy from the shop or from the supplier. So in this example, there's 2 inches of XPS. It's an R10. You have a bag of insulation that's a R12. So again, that's the product as it sits in the bag, wrapped up on a pallet, whatever. That's the nominal R value. The clear field R value is the combination of that insulation within an assembly, including all of the components that are part of that assembly. But it does not include any other transitions. So you get some derating from things like steel studs in this example, a little bit from the thermal clips, but you get the benefit of interior sheathing and air films and air cavities and exterior air films and the other insulation that's in this wall. So it's a combination of all those things as a clear field assembly. And then the whole wall R value is where we start to take that clear field and then derate it by all of these transitions that are occurring on every building. So every building has a thermal bridging consideration, and every building must be evaluated in that way in order to truly understand the value that you're getting out of your insulation. I refer to this as return on investment. So everyone loves to talk about money, and I want a good return on my investment if I invest in the stock market or I invest in a company or a product. I'm investing in insulation. I'm investing in an R12 insulation. If I have a steel Z-gird on the outside of my building, I'm getting a 50% return on my investment. I'm basically losing at least 50% of my value that I've spent on that insulation because of bridging, thermal bridging. So it's very important to focus on these details. This is a picture I took years ago walking around my neighborhood. Again, it's a bit of an addiction, just looking for weird, interesting things, I should say. This is a great example. If you don't have an infrared camera, sometimes it's easy to see thermal bridging yourself, just with your bare eyes. So here's an example of building. It's a stucco building. It's not the most glamorous building, but it is very evident right at the outset where thermal bridging is occurring in this assembly, because it recently was kind of like snowy and wet. The cladding system got wet, and it absorbed some moisture and it became dark. But everywhere that it's light, or where the stucco has dried, there's heat loss occurring. And it's that heat loss that's drying out the stucco. So you can see very clearly every floor slab, you can see every steel stud, you can see the ganged studs at every window jamb and every window head. So this is a very clear example of, there is insulation between those studs, but you can see the impact of that thermal bridging on derating the insulation. Many people, again, have seen this thermal bridging analysis. It's a process by which you apply the clear field assembly, you identify all the thermal bridges, you assign transmittances to each of those bridges, and it returns for you the effective whole wall R value. Now, there are different ways to report that: whole wall, whole building. Does it include windows? Does it include roofs? So that's a bit of a deeper discussion. I've only got maybe 10 minutes left, so I'm going to just keep rolling along. I'm talking here about whole wall R value. So not walls and windows combined as one value, just the walls with all the derating that goes with the walls. I put in here the NECB 2020 Clearfield thermal performance values. I included conversions to R value because some people think more easily in imperial R. These are metric U values in the table. So in zone 5, you have, for your walls, you need an R21, for your roofs, R36, floors, R32. So what happens when I account for thermal bridging? Well, typically, and again, this is where the detailing really comes into play. Typically, it's around 50%. Now, I've seen anywhere from, say, 25 is probably the best if you have really good detailing or not a lot of insulation, all the way up to like 60, maybe 70% derating. So that's a huge swing, and it reinforces the fact that it does not always pay to just keep adding insulation. It's far more beneficial to focus on the thermal bridging problem and solve that problem and get better return on investment for your insulation. So that does a couple of things. One, it reduces cold spots, it improves the overall thermal performance. It also reduces your embodied carbon, because I've seen some instances where we've been able to reduce the insulation thickness by improving all the details. So we actually have a more comfortable building, a more efficient building, a higher overall R value, and less insulation. So it's sort of counterintuitive, but it pays to focus on the details. The other cruel reality of thermal bridging is that it gets worse when you add more insulation. So when you get to that level of saying, well, we'll just add another inch of insulation, you're not ever going to get anywhere close to your return on investment for that. Focus on the details. Focus on thermal bridging. Okay, so what do these kind of highly performant wall systems typically look like? I have a couple of examples here. One is actually one of Pam's and Kara's projects, 230 Royal York Road. This is a mass timber building, but I'm really intrigued by this building enclosure. It's a mass timber panel assembly with exterior insulation, thermal cladding clips, attachment clips, and then some exterior cladding. These are triple glazed fiberglass windows. So I mentioned that I wanted to talk about window perimeter. So the other cool thing with thermal bridging is if you put in a better window, the transmittance at the perimeter of the window also comes down. So it's not just a matter of saying, well, can we just downgrade the window? Yes, sure. Maybe in the energy model, if you're just thinking about window performance, that may be okay if you have room in your energy performance to downgrade to a double glaze, for example. But that will increase the transmittance at the window perimeter, which will further downgrade your wall performance. So these are real kind of like knock-on interplays that you have to be very mindful of. The other project on the left was a project that I worked on up in Vaughan. It's a high-rise building. This is precast cladding. I have another example in a couple of slides where this panel is on a trailer. So this is a large precast unit. It has the window pre-installed in the factory, and then it's hoisted up on the building. And then the sealants are installed between the panels, and the building is essentially air water tight fairly quickly. Anecdotally, I heard from this particular developer that they saved 50 to 60% on their winter heating gas costs with this assembly, because they were able to install it so quickly that they needed so little temporary heat during construction. So I'm not a construction person. I don't have my finger on the bills of what it costs to heat a construction site during winter, but I would imagine it's fairly substantial.
Very much. It's very expensive to cost.
So imagine
And
saving
yes,
50% of your gas
if
costs.
you do that, that would be a lot of money.
Yes, exactly. And corrected is CG Tower by PDPQ. Wonderful project. Had a great pleasure working on that with a number of teams a number of the folks at BDP Quadrangle. So another couple of examples. On the left is an example of sort of traditional built-up assembly system with exterior cladding clips. It's a little bit hard to see. Exterior insulation and then subframing. So this is a great thermally broken assembly. You can see the window and insulation are fairly well aligned here. So there's going to be good thermal continuity at that transition. And then on the right, these are those panels I was mentioning before they're hoisted up on the project onto the building. The opening that's shown on the right there is actually for a balcony. It's not that the window's missing, just so you're aware. Glass values. Again, this is another example where thermal bridging greatly affects the total assembly value. So you can have double glazing certainly in the U of 1.2 to 2.0 range for just the glass. So this is the COG. This is the center of glass U value. You can get triple glazing, again, down to 0.7 or maybe even lower in some cases. But that's not the whole picture, right? You have to put this window, this piece of glass into a frame. In most cases, I mean, sometimes we do structural glass with no framing at all, and that's really great, but not in most buildings. So here's a couple of examples starting at the left, a traditional curtain wall system. The top one has almost no thermal break, maybe about call it a 6 millimeter thermal break just on the nosing of the screw spline there. The other one has a fairly beefy thermal break, enough to accommodate triple glazing. You can get a beefy thermal break like that. That one's probably about 25 millimeters deep at least, maybe a bit more, without having to go to triple glazing, but it just depends on the frame design. In the middle is a metal punch window system with also, again, a fairly sizable thermal break. And then on the right is a non-metallic frame. And you can see even all the cores are filled with insulation. And I want to just state briefly, this is not for thermal performance in the sense that this insulation is giving us a lot of thermal value. It's actually filling the cavity so that we don't have convective losses. So you can imagine the outside in this case will be cold, the inside will be warm. Whenever you have that temperature difference across a cavity, you're going to get this convective loop where the warm air goes out and meets the cold air, drops down, comes back, meets the warm air, rises up. And you end up with this convective loop that basically is driving energy out through the building. Well, filling that with a foam block prevents that convective loss from occurring. There's a little thermal benefit from actually adding insulation there, but it's more about convective loss than it is about the insulating value. So what do we look at when we look at whole system U value? Take the glass, put it in a frame. There are some issues with, spacer bars and things like that, but you get primarily most of the heat flow going out through the frame, which is not really what you want. You kind of want so therefore you need the frame to be very thermally efficient. You have a little bit of loss around the perimeter by the edge effect of the frame, and then you have the least amount of energy, like in terms of U value going out through the center of glass. So this typically would derate the center of glass by, again, 10 to 50%. It's a very big range, but it just shows you that it really matters what frame you pick. And so I would, again, another word of advice, don't always focus on getting the best glass possible. Focus on getting the best frame possible and then putting really decent glazing with it. So, I've certainly seen triple glaze systems that perform worse than double glaze systems because they pick the wrong frame. And so there's a huge embodied carbon aspect. There's a huge cost aspect to that. There's a weight issue. So now you've got more anchors. So there's a whole knock-on effect to picking a triple glaze system if you don't need it. In some cases you do, and that's totally fine. But just be very mindful of the frame because the frame dominates here. I'm going to go quickly through roofing. I don't have a ton of time, so pardon me for going so quickly. You can tell I'm a little excited about getting through all this content.
We'll come back if there are any questions. For sure. Yes.
Yeah. Okay. So on the left, this is a photo I took in, this might have been in Southwest Ontario. Really interesting example of thermal bridging occurring through an inverted roof system. So this is there's membrane on the deck, there's XPS insulation, and then there's filter fabric and ballast. And so it snowed, and all the heat loss coming up through the insulation boards is melting all the snow. So again, really important to make sure you've got maybe 2 layers of insulation and shiplap joints and staggered laps and all these strategies to kind of make sure you have a continuous layer of insulation. And then the other thing that's happening in the background here is you have a bunch of intersecting interfaces. So that thermal bridging idea from earlier in the presentation absolutely applies to roofs. And so you're going to have a slightly derated roof because you have things like penthouses and parapets, and depends whether you assign the parapet to the wall or whether you assign it to the roof. So that's a decision that has to be made in design. But again, just a good example to show that the design of the insulation also matters. And then I have 2 other pictures, again, just fairly generic, saying the influence of the roof on the energy performance is far more substantial on a low-rise building. So anything, I would say, rule of thumb, less than 6 stories, yeah, you're going to be paying more attention to the roof in that case. I had an industrial, lots of industrial projects where, it's a like-for-like roof replacement, and they don't even really think about insulation. It's like, that's a huge missed opportunity because the bulk of that building enclosure is roof. So it's the biggest and easiest upgrade to make, whereas on a high-rise building, you're mostly focused on comfort and a little bit on energy performance for that specific suite that may be directly below that roof area. Okay, let's talk very briefly about air leakage. Again, very, I think, largely misunderstood and mischaracterized aspect of building design and construction in our world today is air leakage. I put in here some system values for windows. There are ways to test this. Keep in mind that when you're speccing AW and CW windows, well, AW specifically, the test pressure is much higher. So it's 300 pascals versus 75 for all other window products. And the leakage rate is the same as at the lower pressure. So it's a much tighter product. So just be very mindful when you're speccing a window. Make sure you're looking at the right air leakage number and the right air leakage pressure. And what are these metrics? So again, there are many, and they're all measured in different ways, which is also super frustrating. So I don't have time to go into the nuances of each of these. There are, various education programs on air tightness specifically, but an example would be Passive House. This is about 0.12 CFM square foot at 75 pascals. You can see lead is measured at 50 pascals, but it's a 6-sided box. It's not just the vertical enclosure and roof. OBC, it's not adopted. They were targeting 2.5 at ACH 50, which again is in the Passive House metric. But you can see that 2.5 versus Passive House at 0.6. Like these are huge discrepancies. BC step code, I think, is at 1 air change per hour. TGS, Toronto Green Standard, is targeting 2 liters per second at 75 pascals, which again is different from the lead requirement. And I did a conversion there for ACH. So it's all quite confusing. There's good guidance from the City of Toronto. I had the pleasure of working on that air tightness testing requirements for City of Toronto a number of years ago as well. You can get that on the TGS website. This is done at the whole building level. So if you have the equipment, the building is of a reasonable size, you can stick 1 blower door in this thing or a couple, depressurize the whole building and measure air leakage. That's preferred. The other option is to do what's called a guarded test. So again, a very simple pictogram of you basically pressurize the floors above and below your test floor to the same pressure. So effectively you have no air leakage between the floors because you've neutralized that plane, and you're only measuring leakage through the enclosure that is on the test floor. So again, we could spend another 45 minutes talking about air leakage, but just to give you a high level in terms of the importance of it, What's also interesting is that in energy modeling, which I also didn't really cover in detail, it's measured at a different metric. So again, make sure that you're getting the right advice in terms of what target to put in your energy model, what target to put in your design documents, and also how to measure it and who to make accountable for it. Okay, I'm going to land this plane. Key takeaways. You will see more opaque walls, so lower fenestration to wall ratio or window to wall ratio, more solid walls, not spandrel panels. So again, there are some ways to make spandrel panels more thermally efficient. Spandrel panels are those opaque portions that are part of a window wall or curtain wall system. Typically, you'll see maybe 30 to 50% window wall ratio. 40 is pretty much ideal. You can get away with a bit more if you have a really good opaque enclosure or really good windows. Again, at a bare minimum, double glazed, low E, argon filled, thermally broken, in a good frame. Focus on the frame. Don't necessarily jump to the assumption that you have to go triple glazing in all cases. And then well insulated roofs matter a lot more for things that are 6 stories and lower. And I can't believe I didn't put the key takeaway here of air tightness. That is, again, I just said how important it is, and I left off my key takeaway. So don't ignore air tightness. It is vitally important. And with that,
thanks, Scott. Just in the interest of time, there are a whole bunch of questions and there are a whole bunch of lively discussions happening in our chat box there, which I think while Kara's going to present her side, maybe if you want to take a look at it, and maybe at the end of the conversation we'll come back and respond to that. I do want to. I get the privilege of actually asking my own question here. Balconies. We've had very hard time with balconies, trying to reasonably solve the thermal bridging. Right? Are we alone, or is that a general situation that, like, if you want to go sorry, for these high performing buildings, there's a very good chance you're going to have to get rid of your balconies, or at least have complications with it?
I think the easiest strategy would make them smaller and put in thermal breaks. Again, if you go smaller, that's less thermal breaks, so the cost savings is there. I'll use anecdotally, I have another project that I worked on a couple of years ago where the thermal breaks allowed the HVAC designer to drop one of the ERVs in each of the, I think it was 2 bedroom suites. So if you improve, so that was a direct trade-off, right? The thermal breaks may have cost $500,000, but they saved $500,000 right off the bat with not having to buy those ERVs. And then in one case, there was another one where the thermal breaks allowed them to get their DC development charge refund. So again, spend $1 million on thermal breaks, get $1 million DC refund. Great. I have a more comfortable building. I have a more efficient building. And you keep your balconies, and it has not cost me another dime. So that kind of integrative thinking, and then I'll just show that top photo is a good example of these decoupled balconies. So these are separately supported, or at least not fully cantilevered balconies, separate from the enclosure, and then connected in a thermally smart way, just with a pin connection at the wall. So just maybe a lateral or something a little bit lighter there.
But nothing are like our traditional cast in place and then window wall sit on top of it.
It's tough. Yeah, it's tough to do that these days. The other thing I would say is the prefabricated bolt-on balconies are also an interesting strategy.
But yes, expensive but good. Yes. Thank you, Scott.
Okay. Thanks.
I think, Kara, I think we're in your hand now.
Okay. Well, first of all, I think everybody can hear me all right? Excellent.
Yes.
Excellent. Perfect. Thank you so much, Scott. And then I also just want to acknowledge Bilal and Samantha in the chat. So we only have an hour to have this talk, and I really wanted to make sure that we had time to go over the key features of an energy efficient building, which will meet these performance criteria, but we had to make content decisions. So I'm delighted to have energy experts answering the detailed energy modeling questions in the chat. And the first thing I want to say about that is that the other reason I don't have a lot of detailed energy modeling content here is that, in my opinion, your energy modeler is a critical part of your design team. So, the number one mistake I see new developers making when they bring an energy modeler on board for their permit model, for their SPA model, for their MLI select model, is to retain that person for just enough labor to do the models that are required for compliance. This person has a model of your building that will help you predict your future energy bills and help you manage your long-term costs. There are definite differences between an energy model for compliance and an energy model for predicting long-term performance. So have that conversation with your energy modeler. But if you bring them to the table, then you can analyze the trade-offs that Scott was just mentioning. You can predict the energy savings and the cost savings, and you can pick the lowest cost path forward. But if you haven't included to have them at the table, to have them modeling the options you're exploring, then you won't be able to get to that iterative lowest cost design for your building. And what Scott was mentioning about building envelope and height and how important the different factors become as, depending on your site's geometry, your building's size. Suite size is a huge one for us in terms of managing different sizes of HVAC systems, or determining which systems make the most sense. If you've got a lot of 2-bedroom units, the solutions are entirely different than if you're all bachelors. Having that person at the table as part of the team, really important. And then the other reason that Scott went first is that only after you have an idea of what your loads will be, can you pick the right mechanical system for the job. So as you're doing these design iterations, start with massing an envelope, have your energy modeler at the table, and then start a conversation about HVAC that includes those items. The other thing I wanted to just introduce is that for improved life cycle cost, it can be really helpful to allow enough time in your design process to iterate through those conversations. Scott was talking about saving $1 million on a DC refund, but you had to have enough time to go explore that option, to do the analysis and figure out if you could get to tier 2 in the city of Toronto, and then go and figure out how much money that would be. If you're trying to race through a permit set of drawings in 8 weeks, then you're going to lose a lot of those optimizations. So you're going to end up with a building that costs more because you went faster. So faster during construction, excellent. Faster during design, to a point,
Not
excellent. But there, yeah, that's right. But there is a minimum amount of time between these phases that's important. And the other invitation I have to everyone on the call is, as we learn to build these higher performance buildings, having a design professional either change their mind or bring a different design concept to the table during the later part of schematic design than they had in the pre-design phase means that they've thought more deeply about your building and found you a better solution, not that they're a bad designer who changed their mind and didn't know the right thing right off the bat, because there's so many different solutions for any specific building. So just an invitation to engage fully with the process and get the best results out of the whole thing. So I'm going to talk about 4 key mechanical measures today. One, that I think most high performance buildings achieving a 40% target will have to include. 1 is heat pumps for heating. 2 is some element of heat pumps for domestic hot water. 3 is energy recovery ventilation. And 4 is reduced corridor ventilation. So these are the 4 mechanical measures that build on top of those envelope measures to give you a holistic 40% reduction. So when we say heat pumps for suite heating, first, why? More important than the energy savings, the coefficient of performance of a heat pump, which measures how much heating is produced by the machine compared to how much electricity it consumed to do it, is usually somewhere between 2.4 to 3.5 to 1. And I'm estimating here based on its seasonal averages. So over the whole year, if you took the amount of kilowatt hours in and the amount of kilowatt hours out. One of the challenges with comparing heat pumps can be that the tests are all at different standards, that they'll be stating their efficiency at different outdoor temperatures, for example. So again, your energy modeler is your partner to look at all of those different cut sheets and then help you compare apples to apples for those different pieces of machinery. But with that said, this is why they're so good for achieving that 40% increase, is that they are getting you better efficiency. So there was a question in the chat about whether or not you could avoid having the same mechanical system in the baseline for your model as in your proposed design. So you're trying to achieve a 40% savings over code. So you've built both a code model and a proposed model. And whether or not you do that, so there are some exceptions listed in the FAQs we've heard from Bilal. By reducing the overall amount of energy that's being used by heating, you're increasing the influence that your other energy efficiency measures can have on the percentage decreases that you get. So that's the benefit for MLI Select performance. And then what's on the screen is the other reason that this is so important, right? You're reducing your carbon emissions by nearly 10 times. Incredibly important in the Ontario marketplace. Thank you, Bilal. Yes, for our Alberta jump, I did scan through the chat. I didn't see anyone from Alberta before making this Ontario-based generalization. So we do have a couple of provinces that are still using quite high GHG sources. So keep that in mind. But in Ontario, this is about right. So heat pump heating approaches from least MLI Select points expected to most efficient. I've just kind of shown a range here. So in the least worst case scenario is in-suite PTACs. A lot of these have very poor cold climate performance. So instead of that coefficient of 2.4, they'll get you sort of 1.8. They're going to be operating on electric resistance anytime it's colder than -10 or -12. Some of them even cut out at -7 Celsius. So there are cold climate versions of this product, but the real reason that I try and sway people away from these kinds of products, whether they're the horizontal kind you're used to in a hotel or the vertical kind, is this giant metal sleeve that goes right through the outside of the building. There is testing by Stephen Winters Associates that shows that the average air leakage through this kind of device is 6 inches square per suite. And so as a long-term owner and operator, you're going to be paying for that heat loss, whether or not it shows up in the energy model. So these are very cost-effective to implement, but they've got serious limitations. There are some cold climate versions coming out of a couple of manufacturers out of Italy that use sleeves through the wall, like 2 cores this size. Those are really interesting. They're only available in a 1-ton peak cooling size. So that is appropriate if you are doing all bachelors, maybe all bachelors in 1 bedrooms. Anything bigger than that, that solution is not robust enough to support a project. It's also a fairly new technology being supported by overseas providers. So there are some people exploring that. You're going to hear about it in the industry. Do your own research and due diligence if you are implementing it. I do have one project that's gone forward with like 30 suites of that, so also feel free to contact me if you want more details. The next one, and I'm including VRF in this, is your mini suite heat pumps. So these, it's hard for me to say for sure from an energy efficiency perspective, and this is again real performance versus modeled performance. We have the option of direct DX systems. One of the major challenges with these for you as a long-term operator, or for your clients as long-term operators, for those architects and consultants in the room, is that the refrigerant transition is very in process. So we phased out a number of refrigerants on Jan 1, 2025. It is only 10 months later. The offerings out there are widely varying. There are some countries that have banned some of the most popular transition refrigerants because they create what some people are calling forever chemicals that we see building up in waterways. So it may be that you'll jump to a piece of machinery that's using a refrigerant that then rephases out sooner than we expect. So these are a solution that gives you really good energy performance. We've been relying a lot on unitary packaged air to water heat pumps to limit the risks of that refrigerant transition for our clients, certainly this year, maybe next year. So this is a packaged piece of equipment because it's got a smaller and contained amount of refrigeration fluid inside of it. We're less worried about that transition. And they can be used with your traditional 2 or 4 pipe fan coil systems. And then obviously the most efficient systems typically in modeling are geothermal systems. So that's the system that Pam and I are using on 230 Royal York is the project that we're going forward with. And they can be coupled to any system you like, but the most cost efficient system is in-suite heat pumps. So for larger projects, that's a vertical stacked. For smallers, there's a variety of unitary equipment. So these will be drilled into 300 to 650-foot wells below the property. There's a lot of practice in the GTA with putting those under the footprint of the building. So they'll often come in first before the rest of the building has been constructed. They'll countersink their wells to below the level of the lowest parking garage, but they can do it with the plain site before any excavation is started. So it really helps with sequencing. And then they come back and hook up the horizontals after the parking garage has been installed. So a lot of work has been done to make those effective in integration. And all of these are the most single important thing you'll do on your HVAC to be able to achieve your MLI select goals. Let's see, I did want to focus a little bit on this air to water heat pump because it might be the newest to people on the call. So this has been
Sorry, Sarah, just before you move on that geothermal, for people who, just two side notes, practical side notes. If you are speccing geothermal systems for CMHC MLI Select, make sure to talk to CMHC people in terms of your contracts for acquiring them and putting them in place, because that's been a changing target. At some point, they were just totally not buying it. Then they said, we agreed. Anyways, that's a moving target. Make sure you know, get into the right contract type for the geothermal field before you finalize your CMHC setup. And I can tell you, based on rule of thumb, and by all means, Kara and Scott, you guys correct me if I'm wrong, we've found that lower than 30 units, it's really hard to make numbers work for these types of bore fields, but 30 is probably roughly where the numbers start making sense to introduce that type of system.
That is a perfect summary. Yeah, I've often heard 100,000 square feet is the magic number where all of the drillers will talk to you, and I think 30 units is a really good lower boundary for where at least some of them will talk to you. Yes,
Yes.
thank you for pointing out that
Sorry to interrupt.
financing. No, that's so incredibly important. Yeah, one of the other things I think that is really worth saying about that geothermal heat exchanger is that if you can take the total number, not as a number for an HVAC system, but as a number in the context of your whole project, it makes it a lot less shocking. If you think about having to finance it directly, which is what some of my clients are having to do to be able to get their MLI select targets, right? You actually have to borrow the money, you have to pay for it, you have to own it yourself. And
Yeah.
taken in the context of this, let me get the MLI select funding and as part of my whole project, the number is not that big. We do find that we
It's not
compare,
that crazy.
no, that's right. We compare overall HVAC numbers for a whole system with Geo to a whole system with, say, an air source heat pump. They're on the same order of magnitude. So we're talking hundreds of thousands of dollars difference, not that like really chunky bottom line number that you will see on a geothermal proposal. So please try and put it in context in your projects. It's not out of the question to finance it. Okay, great. So with that said, on your under 30 unit buildings, what do you do? So we've got a lot of buildings, even 8 units, where we've started really looking at these central air source heat pumps. So what we like about them is that you have one unit that you have to locate. You don't have noise mating machines all over the building. You don't have an array of VRF units on the top of your building. And you can buy them from a wide variety of reputable sources. So if you haven't been digging into the specs on these in the last 6 months, it's worth going back and talking to everybody, because again, that refrigerant transition has actually taken some names off the market and added others. So people who had been already developing new products, that water furnace one up here is a really good example that came on the market in 2025, whereas other people have stepped back. So there are some really good options, and everything that you see on the screen is available to minus 20 Celsius or lower. All right, so climate does impact the same conversation as emissions, depending on what part of the country you're in. So I've got, this is a very fuzzy blow up, but I've got a very fuzzy blow up showing that most of Southern Ontario, you can use any of the technologies we've talked about. But as you start climbing past Ottawa and into northern Quebec, into most of Calgary, you may find that those VRF systems require either a gas backup or an electric backup, or that you may want to consider geothermal because it doesn't require that backup. So make sure that you understand which climate zone you're in when you're picking these systems. All right. On the domestic water heating side, we see more variation. So all our MLI Select programs, program participants have heat pumps for heating, and the great majority of them are using heat pumps for domestic water. So why is that? This is 20% of your overall building's energy use, especially as we dial down the building envelope portion of the consumption. So it's got a huge footprint in your overall energy picture, and being able to get that 3-to-1 energy efficiency really makes it easier for you to be able to implement the rest of your measures. So obviously you can still explore standard technology. We're really liking, again, a central air source heating system. There are dedicated units. They typically will be separate from your heating and cooling, though you can have an integrated plant. You can do heat pump water heaters in suite if your suites are big enough and you have a closet, because they're a little bit noisier, about as noisy as a fridge, and they generate a cooling impact. So if we've got big laundry closets, we love to put those in there. If we don't, then we'll tend to stick to a central technology. And then with in-suite with geothermal, you can implement this as long as your envelope is good enough. And that's again why we let Scott talk first. So if we have enough heating saved in our building from that great tight envelope, then we can just use it, pull it out of the ground and put it into our domestic water system instead. And we've been able to implement that on the majority of our projects, which has been lovely. No matter what, use your low flow fixtures. This is another real surprise from energy modeling. This is usually a 4% savings out of the total 40 you're looking for. That's pretty great for something that doesn't cost anymore. Central water heat pump based systems, if you've never seen a picture, you don't have to go all the way is the other thing. You can talk to your consultant about adding a little bit of capacity to serve a couple of floors or to do a preheat. These are sort of the cheapest one that's out there on the market. They come in only one size and you can deploy them in racks. So I wanted to show you a picture of that one specifically because we've been seeing quite a lot of traction in using that in a more cost-effective way than some of the other products. Energy recovery ventilation, obviously very important. I think most people will be familiar with this. It's incredibly necessary because it gets fresh air directly to suites, which since 2016, the fire code really tightened the amount of gap around a suite door. So we haven't really had reliable ventilation from a corridor to a suite. There's a lot of reasons we don't think that works anyway, but it especially hasn't worked since 2016. So you got to duct your air directly to the suite. And you can, for the same amount of money as a 66% efficient ERV, get an 81 or better. 81 to 84% seems to be the sweet spot. So you're looking for these counterflow cores that are shaped like diamonds instead of the square ones. You're looking for EC motors. So you get those two features, you get a huge boost on your cost, or so your savings without a lot of cost. I like to put an ERV in my amenity spaces because it means I can turn it off overnight or when the building isn't occupied. So again, this is savings for you as a long-term building operator and savings in the energy model. Finally, I also am going to rant about air tightness. So Scott will be able to tell you I've been talking about this for years and years. There's recently been more research that's come out that has said that my interpretation of the study I'm about to show you is played out in large-scale energy modeling. So Kara Lozinski and Marian Tucci, both with the University of Toronto, have recently published some really good papers showing that the energy impact of having interzonal air transfer. So that's to say, all of this blue, text in blue on this picture of this high rise that you don't want, that you're not controlling, the influence of all of that is significant on your overall energy use for the building. So they were able to prove savings in the range of 5 to 6% just by tightening up, especially the corridor to suite transition. So I haven't got their slides yet, so I'm going to show you older slides and see why that wasn't surprising to me. I have this slide from RDH Building Science. So they actually instrumented up this very airtight building. They put a new envelope on it, but it was an old building. So they wanted to know if that actually helped with overall air leakage and let them turn down their corridor pressurization. It didn't. So why didn't it let them do that? Well, it turned out that all of the air they were putting into the corridor wasn't going into suites and pressurizing them. It was just short circuiting right around and going back up the elevator shaft. So when they put tracer gas into this system, they found they had most of the air going up the stairwells and air shafts, like 70% of what they'd paid to condition, right back up the top of the building. Only 20% ever made it to suites. And the bottom four floors of the building were mostly conditioned by parking garage air. So all of this research says that interzonal air transfer is incredibly important. So to control it, your key measures are an air tightness standard for that corridor to wall assembly, weather strip doors, and weather strip doors for your stairwells. And if you can do those three things, then you can implement my next ECM, or energy conservation measure, which is getting your mechanical engineer to turn down the makeup air unit. And so this can be a combination of risk management and energy savings. Put on the drawings and in the energy model the operating airflow that you're targeting, and then size the units so you have a little bit of extra if it turns out that you missed an airflow path. And then how do you make sure that you didn't miss an airflow path? You work with your building envelope consultant, and then you get an incentive in Ontario from Enbridge to cover 80% of the costs of your air tightness testing. And you develop an air tightness testing regime that includes interzonal air transfer. And then you build to that airtight standard to save operating costs and to inform your MLI select model. Okay, let's see. The last couple of things I wanted to leave you with is these are really important. Working with your professionals to make sure that you implement all of the stuff Scott's been talking about to monitor the actual energy consumption is incredibly important, because although our modeled energy consumption for multi-residential buildings in Toronto has increased 6 times in terms of efficiency, the actual energy use didn't change at all. So this is a result from EQ Building. We've actually got Samantha on the call, who I think helped contribute to this study. So if you have questions about it, you can ask in the chat. But they found that space heating, domestic water, common area electricity were a lot higher than the energy model thought. And these were not, and these were not actually controlled by having an energy model that says they were going to be better. We actually have to control them in real life. The other major challenge we are seeing in these high performance buildings with these facades that look just like what Scott presented is that with all that insulation and these windows that we don't have money to put overhangs over, and these tiny little balconies that we've deleted, we don't have south facing overhangs, and we are gently incentivized to increase our solar heat gain because it looks better in the model because it heats the building for free in the winter. But it does that at the expense of like a life safety challenge in the summer if you have a cooling outage and you've got the sun coming in the window. So I have started advocating strongly for ultra low solar heat gain coefficients. I am talking 0.23, 0.18, certainly no higher than 0.32. And think about other ways that you can protect your building from overheating. This is a place where we have, in the upcoming climate emergency, life safety issues. We're going to have 9 months of cooling in Toronto by 2040. So designing a building for a heating climate when we are actually becoming a cooling climate is a real risk. All right, the last couple of slides here. In summary, to hit these targets, use your energy modeler, allow enough design time, air seal your corridors and your stairwells, heat with heat pumps throughout, use 80% efficient energy recovery ventilators, and consider your heat pumps on domestic hot water systems. And then please think about designing for natural ventilation, looking at those low and high openings, and keeping that solar heat gain out so that you have a building that's going to be safe in the summer as well as energy efficient all year round. Thank you very much.
Well, thank you. I feel like we should have scheduled this for a 2-hour webinar. I'm thankful that you guys managed to get it done. We're going to stick around and answer some of the questions if there's anything left in the chat. Just before everyone signs off, we have another webinar scheduled for next month. It's going to be a different topic. It's going to be around using mass timber in your next project, hopefully. And there's a link that I'm going to put there. Feel free to sign in and register right now. But I don't know if you want to, Scott, if you had a chance to go look at any of those questions, or Kara, if there's anything else that we want to go through on the question side of things before we wrap this up.
I do see a great question about open loop geothermal, which is a very cost-effective way to do geothermal in your project. So when you work with your geothermal specialists on any project, they will be able to identify whether it's possible there could be an aquifer under your project. And the next step that's important when you're working with a geothermal expert is to drill a test well below the project to double check what the thermal heat transfer would be through the material below your building. And again, that's the process that will identify a chunky aquifer with enough flow that you could potentially pull that water out of the ground, put it through a heat exchanger, and put it back into the ground instead of having to do a closed loop heat exchanger where you're putting a bunch of tubes and doing energy transfer to the earth.
Interesting. Thank you for elaborating on that. Scott?
No, I think just in summary, like the 35 to 60% seems to be the agreed upon, boundaries mostly for thermal bridging, and also great from Samantha as well, confirming that again we are at least on the same page that it should be including thermal bridging analysis when you do these models, so that you're fairly representing the enclosure performance and getting closer to your actual energy consumption anticipation and matching HVAC and envelope on the demand side. Super important.
Perfect. Anything else? Anyone? If there's nothing else, then we're all good. This is a recorded webinar. Yes, we'll be sharing the replay link and the slides in the next 48 hours. You're going to see another email from us. And as always, please spread the word. Help us grow our impact and get the word out. Thank you, everyone. Have a great afternoon.
Thank you.
Thanks,
Bye.
everybody.